Hello everyone, welcome to this episode on design analysis of algorithms, and in this video we'll learn about minimum spanning tree. Already in the last part we talked about the definition of spanning tree and we learned about a meta algorithm, and we saw now we will see that Kruskal's algorithm and Borůvka's algorithm in part 2, this is the part that they're actually different types of implementations of the same meta algorithm. So let's go over the details once more. So we talked about definition of a safe edge for any component f. If I look at all the edges which are leaving the component, it is a minimum weight edge which is leaving f. And we showed that minimum spanning tree always contains all safe edges. And then we saw all three algorithms, Kruskal, Prim, Borůvka, are different types of implementation of the same algorithm, same meta algorithm. Now we go into more details and we'll discuss about Kruskal's algorithm. So remember again, in definition of safe edges, we look at a component and we look at all edges which are leaving the component. That means all edges which has one endpoint which is part of the component and other endpoint which is not part of the component. In that case, if we look at all such edges, we look at the minimum weight edge, and that is a safe edge. And in Kruskal, what we do is we scan all edges by increasing weights, and if an edge is safe, we add to f. So first we'll just run the meta algorithm and see how it works. And then we'll see a more detailed implementation using union find or disjoint-set data structures. So in this graph, let's say we start with this graph. What is the cheapest edge? So we sort the edges according to the weights. So first we have cost 2. So we'll add cost 2. And the endpoints of 2 are in different components, because right now there is no component. So every vertex is isolated. So 2 is connected this with this. So we can do it. Then the next edge is 3. We again add. And again, 3's endpoint is part of this component, which is already we have made. And the other part is in a different component. It's a safe edge again. All the edges which are leaving. So this edge is leaving this. So in a way, what we are saying is if we look at the safe edges, we are looking at the minimum cost safe edge. So and we are considering the edges in a sorted order. So if an edge, if all the previous edges are already considered, then among all the remaining edges, this is really the minimum cost edge. And if this is a safe edge, if this is both the endpoints are in different components, then it's also a safe edge. So we can add it. So that's what we're doing. 3 added. Then 4 comes again. Both the endpoints are in different components, so we can add it and continue. Then 5 we add, and then we have 8, which is slightly different. Now when we look at 8, both the endpoints are in the same component. So if I add 8 now, it will create a cycle. So it is no more a safe edge, it's an useless edge. So I don't add 8. Then we go to 10. Again, both the endpoints are already part of the same component. We don't add it. Then we go to 12. We can add it. 14, same problem. Both the endpoints are in the same component. We'll not add it. Then 16, we can add it. And then 18, same problem. We cannot add it. 26, same problem. We cannot add it. 30 also, same problem. We cannot add it. In fact, we could have stopped just after this, because already by that time we have 1, 2, 3, 4, 5, 6 edges, and this has 7 vertices. So already a spanning tree will have, with n vertex we'll have n minus 1 edges. So already after having 6 edges we could have stopped. So this is Kruskal's algorithm. Now we'll see the implementation, and again we'll go over the this meta algorithm that we talked about. We'll see the details. So this is the implementation. So this algorithm MST Kruskal, it has input G and weights W. So first we do initialization. So we start with the empty tree. At the end, so we are growing this T in each step. We'll add edges, and at the end we'll return T. This is a spanning tree. We'll maintain. But initially, it's empty. Then for each vertex V, we do make set V. That means for each vertex, we create a separate component. So in this example, let's say we call this A, B, C, D, E, F, G. There are 7 vertices. Each vertex, by make set, this is the operation. We create a new set, Fx, with only x to be the member. So we'll have 1 to be A, 1 to be B, 1 to be C, 1 to be D, 1 to be E, 1 to be F, and 1 to be G. There are 7 different singleton sets. Now we sort the edges into non-decreasing order of weight W. So second step had roughly V make set operation. We'll see the implementation of make set later. And the sorting will take any n log n time algorithm will take E log E time to sort E number of edges. So here I'm using V to show the cardinality of V as well and E to show the cardinality of E as well. Slight abuse of the notation. Now what we do, for each edge taken in non-increasing order, we'll see if the endpoints, 2 endpoints, they're in the same component or not, or same set or not. If they're in the same set, then it's useless edge. Then we'll not add it. If they're not in the same set, then we can add it because it's safe edge. Because both the endpoints are in different components and among all the remaining edges, it's the minimum cost edge. So it is a safe edge. We can add it. And that's why we're doing this T union UV. So we are putting the edge UV in T. And now we are merging U and V into same component. This is the algorithm. Okay, now let's run the algorithm. So now first we take the edge 2. It is the cheapest edge. Now we, in the loop here, when we sort the edges one by one, so we consider 2 first. And we see the endpoints, one is A, one is G. They are 2 different components. In that case, we put the edge UV. So the red shows that the edge is present here. We put the edge and we make sure we do a union of UV. So both the endpoints are now one component. So instead of A and G, now I will just name it as A. This is one component A. In the next round, we have 3. And now we see one endpoint is in A, other endpoint is in C. They are different endpoints. So if we do find set operation, they are different. So we can again add the edge. So now C is again removed and I make sure all 3 together becomes a component, which is this component, which is A. Now we have edge 4 and 4 has 1 in F, 1 in E, 2 different components. So again, we can have find set will provide they're not equal. So we'll make them one component. Then we have 5. We see this is component A and 5's other is B. So they're in different component. We can again add it. So we'll make a larger set. This is 1 and this is another 1. And now the next edge is 8. For 8, when you look at the endpoints, then find set will return it is A for both of them. So we'll not add it. So here in this step, this is equal find set of the endpoints of the edge or edge cost of 8. The both endpoints are in the same set A right now. So it will not be added. Then we consider 10, same problem, both endpoints are in A, will not add. Then 12, now they're in different. One is A, another one probably we have merged when E and F, maybe we could have made it E only. Other one is at E. So then again we can add. And now this becomes a large component. And then next is 14, again, same component A, we cannot add. Then 16, now we are fine because 16, everything else is in A, but this other endpoint is in D, so we can still add it. And we got this to be the final spanning tree. We can continue and finally we'll get this to be the final spanning tree. I hope the algorithm is clear. Now let me again mention the operation make set, union and find set. So make set in the beginning, it creates a set with only X to be the member as A, B, C, D, E, F we tried. When we do union, we are merging these two sets like we had when we merged A and G. G was here, right? So at that time, we merged A and G by the union operation and we make them one component, which is A. And find set, basically each of these sets will have a representative. So A is basically the representative of the component. So when we ask for find set X, then whatever representative of the set where X belongs to, it returns that particular set. And there's a data structure called disjoint-set data structures. And if we use these operations called union by rank and path compression, then it says that if you have n number of make set operations and m number of find set and union operations, you can do it in order n plus m times alpha n times. This alpha is something called inverse Ackermann function. I will not go into detail, but think of alpha is almost a constant. It's not really a constant, but for all practical purposes, it's like, let's say 4. So then if we use disjoint-set data structures, how many operations we're doing here? We're doing v make set and order e number of find set and union. So total operation that we're doing here, which we call m, is order e and n is v. So total this will take v plus e alpha of v. That is the time. And the sorting part will take e log e time. So total you get order e log v time in the worst case, because e log e, what is e? E is number of edges, which is less than equal to v square. So if I take log of e, that is less than log of v square, which is less than 2 of log of v. So log e is order log v. So order e log e is order e log v. This is the value we are getting for Kruskal's algorithm. So if the edges are already sorted, we don't need to do sorting, then actually it's much better. It's just order e plus v times alpha v. Now note that it is not really linear. It's not order e or order, as we discussed for DFS, BFS. There is this added term which is almost constant, but it is not really a constant. Now let me talk a bit more detail about the data structures. I will not go into the detail. I'll just high level, I'll give a high level idea of what the data structure is. And then if you want, you can read CLR's 4th edition, chapter 21, where they talk in detail about this implementation, about the disjoint-set data structures or union find data structures. So in disjoint-set data structure, they maintain a collection S of disjoint dynamic sets. In our case, for example, is vertice SC. In the beginning, there are n one vertex trees. They are basically the members S1 to Sn. And each set is represented by a representative. So in the previous case, A, B, C, D, E, F were the representative. Then we are merging and we are making A is a representative for merging of A and G and so on. In case of make set, we are creating a new set with X to be the only member that we did in the beginning. Union, we unite the sets. Find set, we return the pointer of the representative of set Sx, which contains X. Now this is one representation, which is linked list based representation. So think of this way. Maybe there are 3 nodes F, G, D, and they are in the same component, same set. And then C, H, E, B, they are in the same set. Then this is the representation. So there is one component or set, let's say S1. It has one head and one tail, and F, G, H are elements of this set. Then the head will point to F, and each of the element will have one back pointer and one forward pointer. So forward pointer will show the next element, and back pointer will point to S1, the representative or the set. And then maybe the first element we can call that to be the representative. So head will have one pointer. This is the representative set here, F. And tail will point to the last element here. This is the set. So this is the description here. You can read by pausing. Similarly for S2, we have this. So now when you ask for find set for F, then it will return this. Maybe either S1 pointer, or if you assume F to be the representative, then F. Or if I ask find set for D, then again it will return F to be the representative. Let's say we assume that F is the representative. Then find set D will represent, it will go to this S1 and here, and then return the F pointer. Now to do union, you merge these two and make them same set. Remember A and G we merged, we make them one set. So what we do here, this FGD was as it is, and we destroy this S2, set object S2 is destroyed, and then we add CHEB after that, and then we point all of this, instead of S2 we point them to S1, and then we keep it as it is. So now the representative of the entire this set becomes F only. So now if I ask find set of H, it will return F. In the previous case, find set of H was returning E, but now it is F only. This is the union operation. And you can show that if you always given two sets, you always merge the smaller one to the larger one, always append the shorter list into longer list, this weighted union heuristic. It will take constant time for per make set operation, constant time for per find set operation, and it will take order log n time for union operation in an amortized way. So on average, it will take order log n time. And they showed that a sequence of m operations of type make set, union, and find set, n of which are make set, will take m plus n log n time. And that's what we applied in the, if we apply in Kruskal, we'll get, it will take total m will become order e log v, and this n log n will become, sorry, here number of make sets were v only. There are v vertices. So you will take v log v, and number of operations we had was order e plus v, and then e log v was sorting time. So totally it was giving us this time for Kruskal. But then you can improve further. You can use disjoint-set forest with union by rank and path compression. This is the algorithm I mentioned when I mentioned this kind of best running time for best known running time for Kruskal. In this case, you can represent by some forest, and if I want to merge these two sets, I can just move the pointer of C to F, and then these two sets are merged. So now, if I ask for the representative of H, earlier it was C, but now it is F. And then this path compression makes sure the paths are not too long. So it becomes short, and with some non-trivial analysis, you can show in this case, make set will take still constant operation, constant time per operation, but union and find set will take in an amortized way alpha n time, which is this Ackermann function, and for practical purpose, it is alpha n less than 4. And this will give you the running time that I mentioned for Kruskals. Again, this is a slightly more technical data structure, so you can read CLRS to know more details. But for now, what we need is only this fact that make set, union, and find set takes this amount of time in these data structures. Now let us look at Boruvka's algorithm. If you remember in Boruvka, the same definition of safe edge is there. If for a component, if it is the minimum weight edge that is leaving, we call it safe edge. In Boruvka, in each round, we add all safe edges and then recurse. So think of this example. So now if I look at the vertices for, let's call it A, B, C, D, E, F, G. We begin with all vertex to be isolated component, and then look at the safe edges. So for A, the edges which are leaving is 18, 12, 4. So 4 is the minimum cost edge, so 4 is a safe edge. For G, again, 4, 14, 26 are leaving, safe edge is 4. Now think of D. Then 3, 5, and 16 are leaving, minimum is 3. And for C, it is 5, between 8 and 5. So as you see, sometimes a safe edge is safe for both the endpoints, sometimes it's only for one endpoint, and so on. So what we do is we add all safe edges. So in this case, we see this is a safe edge, 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 and this is a safe edge. So we add all these safe edges. And once we add them, we get two components here. One is this one, other one is this one. And now for these two components, again, we look at the safe edge. In this case, both are 12. So we add this edge and we're done. This is the final tree. You can check the same tree we got from Kruskal as well, because all these algorithms are finding the unique, finding the unique spanning tree. So finally, you are reaching the same thing. Now let's look at the implementation detail. We can use again union set data structures, but we don't even need the complicated path compression, etc. We'll use the first one. So in this case, again, we are given G and W as input. G is the graph, W is the weight. Initially, then we start with empty tree, and for each vertex, we make a singleton set, make set V. This is same as Kruskal. This part is as same as Kruskal. The difference is in this part. Now we run a loop. And while the number of components are more than one, finally we want only one component, everything is connected, we run the loop. And we'll show in each iteration in this loop, number of components half by halves in each round. So it will take at most order log v rounds. Now in this loop, first what we do is for each component, we try to find what is the safe edge. So what we do is first we initiate safe edge to be null for each component. Then for each edge, we look at the endpoints, both the endpoints. If they are in different components, then they are candidates for safe edge. And then we see the present safe edge value for both the endpoints. And if the present edge is smaller than those values, we update. And this way, you can verify at the end of this, for each component, safe edge this array is containing the safe edge for the component C. And then we just update the tree for each component C. We add the safe edge of C to the tree and continue. And then we return the tree. So let's look at the example here. In the beginning, everything is different component, make set operation. Then for each one, we find the safe edge. So as we discussed, these are the safe edges for each component. And okay, let's say we see how they are updated. So maybe for first, let's say this was name A. Let's look at A. Now in the loop, for each edge, let's say we take first 18. We begin with safe edge value for A is null. So if we take this 18 edge, then we see, okay, both the endpoints are in different components. So it is a candidate for safe edge and it's cheaper than 18, cheaper than null. So then we'll replace null by 18 to be the cost of the safe edge. Then maybe we'll consider some other 5 and modify and so on. Then again, we probably come to 12. And now again, we see that both the endpoints are different components and it is cheaper than 18. So we'll update to 12. And then maybe we do something 26. And then finally, again, we come to 4 and we see that 4 is even cheaper. So we update to 4. And we'll see in this case, we have considered all the edges, outgoing edges, and 4 was the cheapest one. So it is the cheapest one. That is the implementation. And once we find the cheapest edges, we just add them. So next iteration, that's what we did. And as you see, the number of components reduces significantly. In the beginning, there was 1, 2, 3, 4, 5, 6, 7. Now we have only 2 components. But at least if you see each of the component, we are adding one safe edge to it. So at least it is 2 of the components are getting connected. So if there are V component in the beginning, it will become at least V by 2. In this case, much better, but it's at least V by 2. So this loop runs for order log V iterations. Now, based on that, we can do the analysis. The update tree, forget about the loop, the entire thing, whenever we are updating the tree, we are adding one edge. And how many times we can do it? Only n minus 1 edges are there, so order n times or order V times. So only V minus 1 union operations we are doing in the update tree. And when we are looking at the finding safe edge part here, the loop is running for log V number of rounds. And within that, we are running it for each edge. So E times log V we are running. And within that, we are finding constant number of times find set operation. So total, loop runs for order log V. And for each loop, we have here order E number of find set operations. Total, how many operations we are having? We are having E log V number of find set, order V number of make set here, and order V number of union. And then you remember the previous theorem that if you use union find with weighted union heuristic, then M operations of make set, find set, union with N make set will take order M plus N log N time. In our case, what is total number of operation? If we sum this, we get E log V plus order V, which is E log V, M equal to E log V, and N number of make set is order V, so N equal to order V. If we put the formula here, we get M E log V and V log V. This is the result, E log V plus V log V. And as E, we are assuming the graph to be connected, so E is more than V. So we are assuming we will also get the same complexity, order E log V, as Kruskal. So this ends the analysis of Kruskal and Borůvka. And in the next part, we'll see Jernik-Prim's algorithm.